All right, everyone, good noon. Welcome to our Monday lecture. So we have 2 more weeks roughly of classes. Go to syllabus, we can kind of see when that last day is. But yeah, we're nearing the end, so hopefully today we'll get through most of the rest of AC circuits. And then we'll get to some optics, and that'll be pretty much everything we've covered. So as far as the differences between, so the final will be cumulative. I'll talk more about that as we get closer. So the final will include everything from test 1, test 2, and then this little bit of extra stuff. And then each week of content will kind of get an equivalent amount of questions on the final. But again, I'll talk about that as we get closer to it. So reminders logistically, make certain you do the physics I care about number 2. That is due tonight at midnight. And I think that's pretty much it. So last class, reminder, we started AC circuits. Quickly kind of going through what we covered is we talked about the form of it. We talked about that 2 classes ago, but that the voltage varies with time, and then the current varies with time. And then last class we talked about this thing called the root mean squared for voltage and current, which basically means you just take the amplitude, the maximum value, and divide it by square root of 2. And that's how you get this root mean squared. And the root mean squared is kind of like this average value, which we had to do this whole squared thing because if you took the average of a sine function, it was 0. But when you squared it, you get all positive values. And so you can actually get an average value. Okay, we then talked about capacitors, and we reminded ourselves that capacitors, as time goes on, so if we look at this one, as time goes on, they get charged up, and as they get charged up, they actually repel more current being put into them. And so the result of that is that current, when you had a capacitor in a circuit, just a capacitor and just the power supply, the capacitor actually had current, so the maximum for current occurred 90 degrees ahead of when the maximum for voltage occurred. So if you were actually taking measurements of the current and you were taking measurements of the voltage across the capacitor, you would find that the current would be maximum before the voltage would be maximum. In the same way, the current, and when it flips the other direction, would be maximum there before the voltage is maximum. So it's by 90 degrees, so the voltage is behind, because time-wise, the maximum for voltage here occurs after the maximum for current. Okay, so basically, there we go. That was our quick summary, and then we found capacitive reactance, which is kind of like, okay, if we're going to treat this like a resistor, this is the equation for it. This only works for AC circuits. And so this capacitive reactance is kind of like a resistance for the capacitor. When you have just the capacitor in the equation, this just acts just like the resistance, and you can find the current if the capacitor is the only element in the circuit. You can find the current if you know the voltage by just taking the voltage divided by that value. Okay, then this was the last question I gave you for clicker questions. And so today, we just talked about capacitors. Now we're going to talk about inductors. So the first question is, when is current maximum in the following circuit? This is a DC circuit, DC meaning direct current, which just means that we have a constant value. So instead of it being AC, so this is something we covered in inductors, which is the last week's stuff. So when is current maximum? For the inductor, if we remember, so the current initially is minimum because as you close the switch, the inductor is going to oppose the change in current. We went from no current to some current, so it's going to oppose that really quick change. So you're going to get no current at first, and then as time goes on, that change in current with respect to time is going to kind of decrease, and so it's going to oppose it less. So this is in contrast to the capacitor. If we see capacitor, it starts maximum and decreases. When we look at the inductor, it starts minimum and increases to the maximum. So remember, inductors and capacitors are kind of inverse of each other. They operate backwards to each other, or opposite to each other. So if we look at voltage and current, so voltage here is our orange line, and current is the blue line. Maybe make that a bit more clear. Voltage current. It shows it over here, but show it at the beginning to make it easier. So now the voltage is actually ahead by 90 degrees. And this is because, this one's a little easier to explain. Remember that the voltage across an inductor, the voltage across an inductor is the inductance times di dt. This was the equation for the voltage across an inductor. That's what it is. Inductance is a constant. And so let's just look at when's the slope maximum here. Well, you see here the slope is maximum right here. So that is max slope of I. So aka di dt equals max, equals the maximum value. And if we look here, the voltage is the maximum value there. Well, let's look at this value. When is it the minimum? Well, the slope here is 0. And look at that. The value is 0 for voltage. So on and so forth. The minimum slope here, I say the minimum, maximum in the negative way, you get the maximum for voltage. So this one's pretty easy to kind of derive. We don't even need to think conceptually what's happening here. But conceptually, what is happening here is, yeah, when the rate of change is maximum, the voltage is going to be maximum across this. When the rate of change is minimum, the voltage is the minimum. So the result of this is that the maximum voltage, or not even max, don't even worry about maximum voltage, the voltage is ahead of the inductor, or of the current, by 90 degrees of the current. You can see here the maximum occurs before the maximum for current. Maximum voltage before maximum current. So the voltage is ahead by 90 degrees. Okay? So the current lags behind the voltage. Okay, so quick comparison. Inductors, the voltage is ahead by 90 degrees. Capacitors, the voltage is behind by 90 degrees. So again, that opposite to each other. And then if we talked about resistors, I didn't make a slide for them. Resistors is the exact same. That was kind of the first thing I showed at the very, very beginning. So resistors are exactly the same. Voltage and current are exactly aligned with each other. The maximums for both happen at the same time. Okay. A lot of information there. But we're going to kind of be using that later to derive some other things. The big things I want you to remember with this, the big takeaways, is just remembering how do inductors work. When do they oppose stuff? Well, they oppose when the change in current is maximum. If you can remember that, perfect. Capacitors. Capacitors have the biggest opposition when the charge is maximum. When the charge is maximum, the voltage across it's going to be maximum. When is the charge going to be maximum? Well, when the current has been pushing in the same direction for the longest time. So current here, maybe we look at this one here. Current has been pushing the same way, so it's getting charge, increasing charge, increasing. Even though this current is decreasing in value, we're still pushing more and more charge. The second the current starts flipping the other way, that's when we start draining charge. All right, and oh yeah, Banter just gave kind of a nice way of remembering this, which is Eli the Iceman, E-L-I, the I-C-E man, and I remember hearing about that one at some point as well, where yeah, E stands for voltage, so I'll even write this down. I think it is a helpful kind of tip. So Eli the Iceman, so E is voltage, L is inductor, and C is capacitor. So the idea here is, so Eli, voltage leads current for inductor, because you can see here voltage is before the current and the inductor one, and then ice, current leads voltage for capacitor. Okay, so if we see here, we can see that makes sense. Voltage is ahead, so voltage leads current. We'll just say leads. We'll keep leads, but it occurs before it. It's ahead of it. And then for the capacitor, it's the opposite. So that's a nice way to remember it. But what are we going to be using it for this class? So quickly, we'll talk about inductive reactance real quick. Remember that the capacitor acted like a resistor? Well, the inductor, if we just have a circuit with an AC power supply and an inductor, it turns out that we can basically treat this inductor like a resistor, just like we did with the capacitor case. And in that case, you get this V equals current times, so remember V equals IR. Well, in this case, it's V equals I times X sub L, which would be I times omega L. So this is basically how much an inductor resists the current in an AC circuit. This is only for AC circuits. And that's pretty easy to see that it's only for AC circuits, because what is the frequency of a DC circuit? It's 0. So you get no resistance there. So basically, just to show the comparison, this is for an inductor. It's omega times L. But for a capacitor, it is 1 over omega C. So this is kind of interesting, because this says that the smaller the capacitance, the higher the resistance, which is kind of interesting. Whereas for the inductor, it's the higher the inductance, the higher the capacitive or the inductive reactance. So again, they're kind of opposite again. If you have a larger inductor, you're going to get more resistance from it. Whereas for a capacitor, if you have a larger capacitance, you actually get less of this. And the reason is it takes, for a larger capacitor, it's going to actually take larger time to put that charge on there. You have more space for the charge to kind of spread out, so the effect is less. Whereas when you have a smaller capacitor, it's really quick for that charge to build up on there. And so when that charge builds up there, the quicker that happens, the quicker you get a resistance to that current. Okay. So pretty straightforward. If I gave you an inductor and I said, and I think that's actually the next question. Yeah. The next question is literally, what is the inductive reactance of a circuit where you have an inductor with an inductance of 3.2 times 10 to the minus 3 henries, and has a voltage of 4 and a frequency of 30 hertz. So the inductive reactance is just omega L. This is angular frequency. If I just tell you in a problem frequency does not equal angular frequency. Remember that F, or it's easier to write it this way, omega equals 2 pi F. So make certain you do that conversion when doing any problem with this. Always make certain you use the right one. And it is important for us to have distinctions between the two, because frequency has more of an actual like real world meaning. It tells you how many times this thing's oscillating per second. So 30 hertz means that this thing has a maximum minimum occurs 30 times a second. So it makes more sense in the real world, but we have to convert to angular frequency for the math. So we oftentimes when you hear about AC circuits, they'll report it as frequency, because it has, again, it's easy to be like, oh, this occurs, whatever the thing may be, it occurs 30 times a second. So in the case of this, the current goes through 30 total oscillations. It reaches the maximum value 30 times a second. But as far as math is concerned, we actually have to convert it to use it in these equations. Okay. Before the break, so normally I give the break right now, but I want to give you all something to think about. So this is a phasor diagram. I'm going to just spend a couple seconds on it, and then we're going to talk more about it after the couple minute break. but the phasor diagram is a utility we use. It's just a tool. So it looks like an X and Y axis, but don't think of it in terms of that. We are going to be kind of using this idea of directions, but the idea is, so here's current. So if we had a resistor, just a resistor, it's the current and the voltage are exactly lined up with each other. You see here voltage and current. So resistor, V and I in phase. In phase meaning if we draw our graph, here's my voltage. In fact, I'm going to use two different colors. Here's my voltage. And there's my current. They're in phase with each other. So you see here, they're lined up with each other. Now remember, for an inductor, the voltage is ahead of the current by 90 degrees. So inductor, voltage ahead of current by 90 degrees. So we draw the graph there, and we say that we'll just draw voltage first. Current is after that. Current, voltage. So look, voltage, we drew an arrow that is 90 degrees ahead of that. And the very last one, capacitors, voltage behind current by 90 degrees. So if we draw the graph for that, now our current is the one that starts there. And so we get voltage and current. And if we look at our nice graph, we see that it is also the voltage for the capacitor is 90 degrees behind. So yeah, this is a vector representation. So that's a good question by Paul. He asked if this is a vector representation. It is. It's kind of weird because these axes don't actually have a units associated with them like this one does, the vertical one, and I'll talk about that a little bit after. Basically, this one is like just voltage, but this one here does not. And basically the idea is as time goes on, this whole thing rotates and spins around as the current changes its maximum value. So this side is also current. It's a very weird kind of diagram. But just think of it in terms of this like idea that, oh, we just put the vectors with respect to each other. And then as the current's rotating, they all kind of rotate with it, where the voltage of the inductor will always be 90 degrees ahead, voltage capacitor will always be 90 degrees behind. And we're going to use these vectors. So just kind of sit here, try to digest this. Just right now, just focus on the idea that the inductor is 90 degrees voltage ahead of the current. The capacitor voltage is 90 degrees behind the current, and the resistor is aligned with it. And if you're okay with that, then the next step will be pretty simple, which is the idea of it just kind of spinning around. So go ahead and give you all a couple minutes. I'll go try to find my dog. And if you have any questions, please post in the chat, but feel free to kind of review some of the stuff we talked about with the inductors. See if anything doesn't make sense, and if anything doesn't make sense, or just you have any general questions, please let me know, and I'll answer them in this time. Sit. All right. And for now, I'll make this bigger, so there he is. All right. So holding true to our thing. It's a nice, if you all don't get to see me in person, at least you get to see my dog, so maybe that's some consolation. Okay. So Jacob asked, how can a graph not have anything on the other axis? That's because this isn't really a graph in the usual sense. That's why I said this is more just a tool. So we kind of think of these as vectors, but from graphs, from having axes, but it's not really, we're not really graphing something like we normally would. So it's weird in that way, but that's where I'm just like, just focus on the idea of like, imagine these are vectors, and we're just looking at the vectors with respect to each other. Yeah, it is. Think of it like a polar coordinate system is actually pretty useful. But what's interesting is, yeah, we're still going to kind of reference, and I'll get to the kind of that next step of that referencing it with respect to this axis. All right. So, now that maybe some things have settled, maybe you have some more questions on it, had some time to think about it. So the other piece of this is that this whole thing will kind of rotate as time goes on. So I'm going to take this and show it in the next slide. I'm going to make a new slide to show this. And all this thing is, we're using this as a tool to kind of understand what happens if we put a resistor, a capacitor, and an inductor in a circuit all together. That's what we're using this tool for. So before we just had the resistor by itself, just a capacitor by itself, and just the inductor by itself. But we're going to use this as a tool to see what happens when you put all three together. And that's really what this is, just kind of a conceptual tool. So imagine that this is, at some time, what the current looks like. Well, at some later time, we could draw it. And now, at some later time, maybe current, well, I say maybe, it's going to happen. Current has now rotated. So current is, but when we say rotated, because this is the value of the current at some time. So maybe even it's better if we draw this a little bit lower. So here's my current. So let's go ahead and draw all the other vectors for it. So the current is here. So the voltage for the, and I'm going to use red, voltage for the resistor is right here. The voltage for the capacitor is still behind by 90 degrees, and the voltage for the inductor is still ahead by 90 degrees. And the idea here is we can just take the intercept with this y-axis, and unfortunately, I put that in the way. The intercept with the y-axis gives us the current at that time, the voltage of the capacitor at that time, and this one here is the voltage of the resistor at some time, and the voltage of the inductor at some time. Okay, and you may be like, well, why don't we just use the magnitudes of these? These vectors, these voltage ones are constant, and these represent the max voltage on resistor, max voltage on capacitor, and the maximum voltage on inductor. Because the idea is, and so if we looked at here, the maximum value is the peak, the amplitude, but you see here the voltage changes with time. As time goes on, that voltage increases and decreases, increases and decreases. And so when it increases and decreases, we can see here as this spins, as this voltage for the resistor spins, this VRT will increase until it's a maximum when the voltage across the resistor is maximum. And then the same thing, the voltage across the inductor will actually decrease, and be a minimum here. And so as this thing spins around, each individual element, the resistor's voltage will increase and decrease over time. The capacitor, the actual voltage in the graph, so if we took the graph of the, and this is where it's tricky, I'll draw this graph kind of a little bit later. The final graph of all three together, the voltage across the capacitor is going to increase and decrease. And the voltage across the inductor, this Y value is going to increase and then decrease, and then go up to here. And so you get each element gets a sine wave associated with it as this whole phasor diagram spins around. And as it spins around, the current also increases and decreases. So, why are we doing all of this? Why are we using this phasor diagram? As I mentioned, it's to combine the vectors. It's to give us an idea of what happens when we combine them all together. Because what we can nicely do is to get the net effect on voltage, all we have to do is add these three vectors together. All we have to do is add the resistor vector with the inductor vector with the capacitor vector. And this is going to be easily seen. So how do we do this? So let's draw our draw that phasor diagram. And we're going to draw the easier version. So we're going to have the voltage of the inductor straight up. We're going to have the voltage of the resistor to the right, and we're going to have the voltage of the capacitor down. And remember, the current is chilling over here with the resistor. So we just drew, this is the easiest way to draw it for addition. We could have done it in any orientation. We could have spun it and add the vectors that way, but this is really easy to add up and down. And again, we imagine that these were like X and Y components. So treat each of these like a vector. How would you combine these components? How do you combine vectors? How do you add vectors together? Well, to add vectors, step one, add parallel, anti-parallel vectors together. Okay. Sorry. Yeah, so really quickly, someone asked, can I repeat what this current is? When the current is over here, so the way we actually get the current in the graph is we take the intercept, so take like a dotted line, find the Y value, if we call this like Y value. This is the value of current at that time. So this is the maximum current possible. But then the current at some time is the intercept with the axis. So as time goes on, the current increases and then decreases. And then it becomes negative. And that negative value increases and then it decreases. Sorry, I have to keep switching hands because at some point my hands can't rotate anymore. So the intercept is the current with respect to time. Okay, so as far as adding, we're going to add our vectors together. And we're just adding voltage vectors. And then we'll add perpendicular vectors. Okay? Because that's just how you add vectors. Imagine you add all the X components together and all the Y components together, and then you add the perpendicular vectors. So let's go ahead and add our two, and just to clarify, this is the origin. Let's add our parallel and anti-parallel vectors. So our ones here, we can add VL. So VL minus VC. We imagine those are like in the Y component. Okay? And then our X component is just VR. If we think of this in X and Y, they're not X and Y, but we're just going to use that notation because it's easy to add vectors. Okay? So how do we add these two together then? They're perpendicular. Well, the net vector will be the square root of x squared plus y squared, which is going to be square root of VR squared plus VL minus VC squared. That is going to give us our net voltage equation. And here's the part that maybe will seem a little weird. Let's see if it's in the next slide. Yeah, so it's in the next slide. So there we go. So that's our voltages added together. That's going to give us the net voltage vector. So if we did that graphically, let's just go ahead and show that over here. So our VL is this way. Our VC is this way. And then our VR is this way. So our net vector, tip to tail, is going to be this direction. So this is VL, this is VC, this is VR. All I did is I took the vectors here. VC could be larger than VL in certain circumstances. Like these vectors are arbitrary that I drew here. If your inductor is bigger, then this will be bigger. If your capacitor is smaller, or I think bigger actually, this could be bigger. I just, based on the vectors I randomly drew here, this one happened to be smaller than this one, but that's not always the case. And so I just did tip to tail, so I drew VL. I didn't draw it exactly on top of it, but I drew VC. Technically, if I wanted to be more accurate, VC should be kind of as close as I can draw it to this. VC is right there. It's kind of hard to draw. I'm going to draw it off to the side again. There we go. And then VR is like this, and you still get roughly the same way. Same answer. So that's what the direction looks like. How do we get, because now what we're going to do is let's plug in, remember that just V equals IR, V equals IR, or V equals IXL, or V equals IXC. Okay, they're all in series. This is what our circuit looks like. It's an AC power supply hooked up to a resistor, a capacitor, and an inductor. In series, current is constant. So the current through this one is I naught, the current through this one is I naught, the current through this one is I naught. Whatever the current value is, they're all the same. So if we plug in, so they all get the same current, you can pull out the current here. And now we get this expression where our V equals I times, we're going to call it impedance. Z here is impedance. And we just derived it. It's R squared plus the inductive reactance minus the inductive capacitance, that whole thing squared. And if you plugged in what each of those are, omega L minus 1 over omega C. So this may look complicated, but basically what I want you to take away from this is that if you have a resistor, a capacitor, and an inductor in a circuit together, or any combination of the three. If I had a resistor and a capacitor, and inductor, or a capacitor and an inductor together, this is how I get my net resistance for the circuit. We call it impedance, but it's basically acting like a resistance. And that's going to show up, this next slide is still impedance. It's how much current is resisted in a circuit which has some combination of resistors, inductors, and capacitors. See here, the voltage equals I times Z, which is just like that V equals I times R. Because we're working with AC stuff and we saw that inductors and capacitors actually oppose the current in these circuits, we now have to account for them, and this is how we do so. So no longer, if you want to find current, do you just use resistance? You actually have to use all three of them. And this will give you what the voltage will be at some time given some current. All right, given the impedance, you can find the voltage in the whole circuit across all the elements together if you know the current at that time, or vice versa. Okay. So, very quickly, I'm going to kind of run through the last few things. I'm going to cover them again a bit more. But I did give you all this last one. Oh, so this is the last quicker question I gave you, which is what is the net impedance of a circuit with a frequency of 120 hertz, which has a 13 ohm resistor and a 23 microfarad capacitor in series. So this circuit does not have an inductor, so the value of the inductor, no inductor, so XL equals 0. If you had no capacitor, the inductive capacitance would be 0. Okay? So if you don't have an element in a circuit, if you don't have a resistor, or you don't have an inductor, or you don't have a capacitor, whatever that element in here would be, would just go to 0. No resistor, this goes to 0. No inductor, this goes to 0. No capacitor, this goes to 0. You may think that if we don't have a capacitor that C equals 0 and this goes to infinity. That's not the case. So if no R, R goes to 0. If no L, omega L, and in fact, I'm going to write this XL goes to 0. If no C, omega C goes to 0. Okay, that's an important thing I want to clarify. Can I show you the voltage of my feet? I don't think that means anything. All right. Well, you all have a good rest of the day. If you have any questions, just let me know. Please start doing the problem set problems for this. But otherwise, we just have a tiny little bit extra to cover. And we will finish that up next class, no problem. Probably in the first half of the class. And then we'll actually move on to optics, which is our last section. So we're getting through there, getting things done. Yeah, and again, please continue working on the problem sets. Please continue studying things, and if you have any questions, let me know. All right, have a good rest of the day, everyone. Oh, and I'll be doing the clicker questions for the last class after this as well. So if you want to, I'll post a link for that, and you can view that as well. All right, goodbye.